Okay, so we have come to the last part of BMS design and embedded system. How to develop algorithm. Most of you would be using the MATLAB. If not MATLAB, then several other softwares are available, commercial one as well as generic one like Scilab also you can use. There are very dedicated softwares for this, like GT is one of the GT Suite is one of the software where you can again model the whole battery pack, can check its algorithm. But what I have done in next 1 or 2 slides, that use MATLAB Simulink model to develop the battery algorithm as well as your embedded software. You can also do hardware in loop simulation for your software as well as your for hardware using the MATLAB and some separate hardware in loop simulator, a small simulator. So what you have to do, you can put the complete model, you can build up your complete model in the MATLAB. You can build all the logics using the state flow module of that one. And then you can also select the microprocessor. It has an inbuilt library of microprocessor, or you can talk to the microprocessor vendor. They can give you the equivalent MATLAB simulator in that, and then you check all the logics of your BMS functionality, SOC, SOH, sensing, and then what you can do, you can write scripts and check all the functionality on the software, that we say software in loop simulation, and can generate the C code which can be directly fed into the your BMS, and can also use the hardware in loop simulator without even putting before the into the BMS. Check all other functionality. So what happens in that, the chances of error in your actual prototype becomes minimum, and it also gives you a nice overview of how your logics, programs, algorithm is working fine. More on that you can go. One of the things is MATLAB. You can do the similar things on other platform also. There are several platforms available for that to do quickly. This is one of the shortcut way. There is another way. You develop a hardware, full hardware, then you develop the parallel embedded system code. You flash those codes over the hardware, build a battery, and check all the things together. If there is a fault, you again rebuild that hardware, or rebuild the prototype, or change the components what is need to be changed, change the software to your desired level, and again retest, and that's another. And most of the people follow this second approach. However, at learning level, using some software like MATLAB, you can understand the system very fast. So next move, how to build a battery pack. Connect the cells into the module using MP-NS theory. Now connect all the modules to bring desired voltage, capacity, and the current. Then place the fuses wherever is required for protection. Build the energy delivery path using the contactors, relays. Develop the BMS hardware as well as software. Connect the various sensors like temperature harness, voltage harness with that. Put it into the casing. Connect with the service port. You may require different sensing devices, temperature, voltage, Hall sensors. Connect all those things, pre-charge circuit to the service outlet, and then finally you put it in one casing and start testing. Now everything if satisfied, you have several other constraints: packaging, weight, energy, and if all the things are satisfied, then what you do? These all are performance testing. Then you start reliability testing. When we say reliability testing, you run for thousands of kilometers. If none of the problems are recurring, you are okay. Wherever you find some problem, you come back, rectify that problem, start rerunning. We do various tests of AIS standard, ISO standards, SAE standards to confirm the reliability as well as performance. And once you are done with this course, you would be able to build this battery pack till level. Obviously, you need to read much more, but a basic battery pack can be built upon this like this. Then testing, performance testing, and then reliability testing, which you can continue. If there is any problem coming up, come back, check the errors, rectify those errors, and start going back. Now next is software architecture. What we have in the BMS hardware, we have a hardware abstraction layer known as HAL. Now we have database, we have protection module, we have application module, and then we have application drivers. And this HAL communicates each of them using the various communication, SPI mostly, or through CAN. And then each of these applications also keep on talking with each other. So if application required some sensor value which is there in the database, is collect from that place, calculate the thing, and throw back the result to this application driver does that, and then throw back it to application. When application is done, everything is under the protection or not, it communicates to the protection gets enabled. The protection can directly also fetch the data from database, which is from the sensor, and can take action on the protection side. So let's summarize the BMS design. A well designed BMS should have good resolution for the measurement at the cell and the pack level. When I say measurement, what are the things we measure mostly? Voltage, current, temperature. You can have other things also like insulation monitoring, isolation monitoring, pressure monitoring, vibration monitoring, that can be add on. But whatever we measure should have a good resolution of measurement both at the cell and the pack level. It's important to maintain the equal SOH, state of the health of each cell at the same level. When I say cell, that means capacity fed. So there has to be equal capacity fed over the time on all the cells. If there is a differential capacity fed, then that becomes a problem. You cannot get the full pack capacity or full pack energy, because in most of the in the lithium ion battery pack, weakest cells become dominant always for capacity calculation, SOH calculation, or SOC calculation. So that weakest cell makes the pack unsuitable, and that weakest cell could be one, rest of the cells are still fine. Highest safety level, actively shut down in case of extreme scenarios, so that main and machine both are, main machine and environment all are protected. Keep predicting and the warn users. If you are not if any degrading events are happening, there would be a regular degradation which you already know, but anything which is accelerating that, keep informing the user by logging those functions or those data and giving back it to the user that this thing has happened and this cell is getting degraded faster than, so that corrective action can be taken either in that design or in upcoming design. If possible, control the auxiliary system directly or through by communicating with the auxiliary system control system, so that the pack efficiency is maintained at the highest always. Like if a thermal management system, you wanted to keep the temperature between 15 to 35, it should always do that. It should communicate, my temperature is rising, please start, or if you are already working, start working extra, so that my temperature should come down to that level. It can measure, it should measure voltage, current and temperature, and calculate SOC and SOH. These all are fundamental parameters. It should, wherever there is a possibility, if in the case of HV high voltage pack, isolation monitoring. In case of very heavy and very reliable, if you wanted to make a more reliable pack, pressure, vibration, and all depends upon the cost and the functionality. It should measure. It should maintain connection or communication with ECU, electronic control unit of the vehicle, so that it can say, yes, I mean good, I have this much of charge, I can run the vehicle for this distance. It should communicate with the motor, I have this much of energy left, I can give you only this much of power, or you are overdrawing the power from me. Sensors feedback, it should be able to communicate with the sensors. It could be one way or it could be bidirectional. Like for temperature, you just wanted to communicate one way, from the sensor information should go. But something like IMD, it should communicate. As soon as IMD says things are not good, it should communicate, okay, shut down. It should communicate with the slave unit, bidirectional. It fetch all the information from slave unit, and in case of any event, it should also direct, that's okay, you shut down. Avoid the battery packs from BMS. BMS should avoid in case of any abuse, in case of accidents, like if vehicle has toppled up, it should disconnect. In case of thermal runaways, what could be the preventive action? It should give the proper log of each and every activity, so that you can diagnostic, you can run analytics, you can take design upgrade in your next version of the product. So with that, I end the fundamental design of the battery pack. In case of any question, please write to us. If you do have any questions now, you can ask right now.
Which is at a high voltage, in order to come down to lower voltage, it will have to give up current, no? So where does that current go?
So that energy which get wasted as a heat. Yes, that energy get wasted as a heat. That's why it is known as passive balancing. In active balancing case, we use that energy to bring other cells up. So from here it is coming down, other cell is coming up. In that we don't waste energy, but in the passive balancing we just use a resistive load to bring down that energy, and that resistive load is nothing but it's a heat, it's converted into heat. So what we have done till now is the fundamentals of battery pack design. In that we studied electrical design, mechanical design, thermal design, and the BMS. In the next class, in the next section of this chapter, we will start with the testing of the cell and the pack. The fundamental things what we do is characterization of the cell and the pack level testing. So, in the next section, that's what we will discuss, and with that this chapter will end, and that would be taken care by our teaching assistant Sushant. Okay.